Hey, this is a quick video that walks through simple linear regression for folks who might need some additional help with it. So we'll start out with a data set that has a set of x's and a set of y's. And what we're going to do is we're going to look for the relationship between x and y, and we're going to try to predict what do we think y will be when x is some value. To start out with this, we need data. So we will have a set of x's that are 8, 10, 10, and 6. And the matching y's are 100, 150, 125, and then 100 again. To save ourselves a little bit of time, I will go ahead and say y bar, so the average of the y's, is 118.75. And the average of the x's is, where'd it go? 8.5. Cool. So what we are going to try to do in this scenario is simple linear regression. I want to fit a model where I say y is equal to beta naught plus beta 1 times x1. I only have one x, so I'm just going to denote this as x from henceforth, but that's what it is. And to do this, I need to find two coefficients. I need to find a slope coefficient that tells me how does y change as x changes, and I need to find an intercept that tells me what is y when x is 0. The formula for this, and we are going to use the least squares method. The formula for our beta 1 is the sum of x minus x bar multiplied by y minus y bar over the sum of x minus x bar squared. And this will give us an estimate of beta 1. So from our previous page, we are going to need these values and these values. So I need a set of differences for each of these, and I will set this up here. I will say x, each of our x's, x bar and then the difference between these two. Well, I won't square it at first. So the difference between 8 and 8.5 is negative 0.5. 10 minus 8.5 is 1.5. Again, it's 1.5, and this is a negative 2.5. For our y's, we will do the same thing. Cool. So the first y was 100. This is 118.75. So the difference here is negative 18.75. The second y was 150, 125, 100 again. So this is 31 and a quarter, 6 and a quarter, 18 and cool. So with these things, I have all of the parts that I need for this equation. I have these differences, and this, which is just this term squared. So, the top part of this is going to be the sum of x minus x bar multiplied by y minus the average of the y's. The bottom part is going to be x minus x bar squared. For the first observation, this is negative 0.5 multiplied by negative 18.75 plus 1.5 multiplied by 31.25. So this multiplied by that. And we repeat this process for all 4 of our observations. And I don't know if I have room for this last one, so I'll write it here. The denominator is just the values in this column squared and then added together. So negative 0.5 squared plus 1.5 squared plus 1.5 squared plus negative 2.5 squared. The top part of this, if I were to add all of these numbers together, is 2.5. The denominator is 11. So 10 point, we'll round it to the second decimal place. 10.23 is my slope coefficient. Okay, so beta 1 hat. My estimate of the slope of this line that we were projecting from before is 10.23. Now I need to find the intercept term. The way we find the intercept term is we are going to take the average of the y's and subtract off of that whatever we've estimated for beta 1 multiplied by the average of the x's. We can do this because we are doing regression through the mean. So this is 118.75 minus our 10.23 that we got for beta 1, which comes from here, multiplied by 8.5 from before. This is 31.82. So if we go back to the projection of our line, we're saying this is 31.82. Ignore the 5. All right. So if we were to interpret this, we would say we expect for a 1 unit increase in x to see a 10.23 increase in y. Alternatively, we could plug in some value of x, and then I could say this is what I expect y to be when x is whatever value I want to look at. And we'll look at that in just a second.